Hi, welcome to the sorry for the delay for 2 minutes. So this is the ninth live session of Points of Topology 1 NPTEL course. Before starting, let me know whether am I audible properly. Okay. So okay, 1 minute. Okay. Before starting, let me know do you have any question or any doubt.
Why connected metric space?
Yes. Yes. Continue, please.
Why connected metric space having more than one point is uncountable?
Okay. Connected matrices must have more than one person. 1 minute. Hmm. So why connected metric space having more than one point is 1 minute. 1 minute. Let me 1 minute. Okay. Oh, okay. So why can't a matrix is having more than one point is uncountable? So the argument goes as follows. 1 minute. So um let okay. Uh, huh. So let x comma b is a be a connected metric space having more than one point. Okay. Now we need to understand why this has to be uncountable. Correct. So suppose more than one point. Suppose it has 2 points, right? So we have 2 points x naught y naught belongs to x. Of course, x naught not equal to y naught. Correct. So what we can make? We can give constant function from x to r, where each x shall go to d of x comma x. Okay, call this map g. Okay. So this tells that g of x naught equal to 0 and g of y naught is equal to d of x naught y naught not equal to 0. Okay. So this tells what? This tells that image of g has at least two distinct elements. Okay. But observe that since x is connected and R is compact, so this implies image of G must be an interval. So this implies what? This implies G. So this implies what? This implies image G must be uncountable. Okay. So this tells that X has to be uncountable, which is quite obvious. Okay. So 1 minute, please.
And next question,
Yeah, please.
why Sn
Yeah, okay.
minus countable point is connected?
Okay, before going to the previous question, this question, do you understand?
Yeah, yes, I understand.
Okay. Okay, so can you please repeat your next question?
Why Sn minus countable point is connected?
Why SN minus counter is connected? Why SN minus counter point connected? Oh, 1 moment. Okay. So is it working properly? Okay. So hmm. so um, look. So you need to show connected, right? So if you so claim is not only connected. Claim is Sn minus countable point is path connected. Okay. Why so? Because since why so? Because Sn is uncountable, right? Correct. So this implies what? This implies between any 2 points of Sn, there exist uncountably between any 2 points of Sn, there exist uncountably many paths. Correct. So this tells that so look. So you have basically 2 points, and there are countably many points outside the consideration. Okay. Now, if you take it on, there exists uncountably many paths between these 2 points. Okay. Now, since there are uncountably many paths, so there exists one path which does not intersect all of these countably many points because there are uncountably many paths. So yeah, so that is the argument, correct? So this tells that there exists one path which avoids those countable points, those countable points. Okay. So yeah, so this is the argument. Do you understand, Mustaq?
Yes, yes.
Okay. Do you have any more questions?
No.
Okay, thank you, Mustaq. Okay, in the meantime, if you have any question or doubt, please stop and ask me. Okay. 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 So there is one interesting question. The question is that give example of a space. Give example of a space which is which is limit point compact but not compact. What is the question? The question is give example of a space which is the limit point compact but not compact. Okay, 1 minute. 1 minute, please. So, so, so what is the limit point compact? So limit point compact means what is the definition of limit point compact? Can anybody please tell? What does it mean by limit point compact? That is every infinite subset of X has a limit point. Limit point compact means every infinite subsets of X has a limit point. This is what we mean by limit point compact. Try and think about to construct an example which is limit point compact but not compact. Okay. Take your time, think about it. I shall be back within a few minutes. Okay. So is anybody able to find some construction example which is limited compact but not compact? So who is the Sumesh or Mustaq? Anybody? Please can construct some example, or at least can you please give tell the idea how to approach this type of problem? So see, so first point is that uh, so first observation is that you cannot take any topological space which is not metrized. Okay, because metric space has this property, namely, 1 minute, let me write it down. So first hint is sorry. uh, So first hint is that what that um, constructs construct or find. Basically, basically no need to construct such a space. Actually, you need to find only space. The space already exists. Okay, so basically find a space which is not metrizable. Okay, because metric space has this property. So yeah, so now try to find out. So there are many, so there are, so we have seen many examples of some of spaces which are not metrizable, correct? Uh, so so try to understand also. So look, we have seen some examples of co-countable topology, co-finite topology, and we have seen examples of lower limit topology, K topology, that then that S suffix omega, that one. There are many examples we have sure. So within the example, try to, so there is few examples within that which will be limit but compact but not compact. Okay. So try to think and let me know what will be the possible answers for this question. Okay. So you no need to construct any typical example. So only you need to observe the previous examples that you have seen will work actually. Just figure it out. Okay. Okay, please try and let me check other questions also. If anybody, if two of you, yeah, if anybody out of two of you has solved, please let me know. In the meantime, I am finding other things. Anybody? Okay, okay, okay. So okay. So let me. Okay. So look. So there are many counter example for this. Okay, and there are some really difficult counter examples. So let me for this type of counter example. First, let me write down the most easiest one in order to make it clear. Okay. So the counter example is as follows. Okay. So consider so take the space X to be Z plus cross 0, 1. Okay. That Z plus is a positive integers. Z plus are positive integer set. Okay. X equal to Z plus cross 0, comma 1. Okay. So so this is the space I gave. Now check two things. Firstly, this space X is not compact, but X is limit point compact. Okay. Now of the space X is given, now try to understand why it is not compact, but why it is limit but compact. Okay. Now I expect that this will be easy for you. So try and convince yourself and let me know. Okay. And if any point of time you are not understanding things properly, please ask me. And in case if you are done, please unmute yourself and describe the and give the argument. Okay. Okay, when you are done, please let me know. Okay, so it seems that it is okay. So let me explain that why the given X is not compact, but it's limit but compact. Okay. Well, it seems to be very much trivial, but the argument is quite tricky argument. And this type of questions might come in exam also. Okay. So let me give the argument. Oh, 1 minute, please. The app is not working. 1 minute, please. Okay. So, okay. So, firstly, for this one, why X is not compact? Because the open covering UN is equal to singleton n cross 0 comma 1. This open covering does not admit any finite. This open cover does not admit any finite subcover. Okay, so this is the first and second. So that's why this is no compact. And second is that observe that uh, every non-empty open set of X has a limit point. So this is the second one, okay? So yeah, so that is the argument. So what is the first argument? The first argument is that since X is not X is not compact because every open covering. So since the open covering UN is equal to n cross 0, 1, this open covering does not admit any finite subcover. Okay. Secondly, is that every non-empty open set of X has a limit point. Okay. So yeah, so that is the so these two are the argument. Okay. So okay, till now, does anybody have a question or any doubt? Please let me know. And now, well, after this argument, let me give you some little more complicated examples because you know what topology deals with some kind of abstractness. So the next example that we are going to deal with is somehow quite abstract and complicated also. So let me discuss that also. Okay, it is known as infinite ordinal set. Okay. Oh, anyway, that's not the name is not important. The construction is important. Okay. Okay. So before going to that, let me know. Do you have any question or any doubt in for this question? Please let me know. Okay, it seems there is no question. So let me. Okay, so let me give the argument of the next example. That okay. So this one is that um, consider the minimal uncountable well ordered set S omega. Okay, in the order topology. Consider the minimal uncountable well ordered set S omega in the order topology. Okay. Now S omega is not compact. And second thing, try to show that S omega is limit point compact. Okay. So this is a definition of S omega. Okay. Now try to show that it is not compact where it is limit point compact. Okay. Try to think about it and let me know the argument. Okay. I shall be back after a few minutes. In the meantime, please think about. Okay. I shall be back after a few moments. Okay, so okay, so first, before proceeding to give the answer, let me know. Are you able to convince yourself that whether S omega with this order topology will be not compact but limit but compact, something like that? Are you able to convince yourself? Because the argument what I am going to give is highly abstract. So first you need to convince yourself whether this is the case or not. Okay. So first, okay. So for that, first let me convince yourself whether this is true. Okay. So firstly, what is S omega? 1 minute. Yeah. Okay. So what is S omega? S omega is nothing but what is S omega? S omega is nothing but a minimal uncountable ordered set S omega. Okay. So if we consider this line, we can take this line to S omega, correct? And it is minimal uncountable ordered. So okay. Now let me explain why it is not compact. Okay. So the argument will be quite abstract. So in order to understand this argument easily, instead of the abstract some kind of minimal uncountable set, we can consider real line, which is which is obviously uncountable, and then we need to do the same argument what we shall going to see in this S omega case. Okay. So let me write down the argument. Okay. So uh, so first we need to show it is limit bound compact. Okay. So for that, what we need to do? So we need to show any infinite set must have a any infinite set have a limit point. Correct. So what we are going to do is the following. So let A is a subset of S omega. Okay. And let A be infinite. Okay. Now choose a subset B of A that is countably finite. 1 minute. Let me write it down clearly. Okay. Hmm. So choose a subset of A that is countably finite. Okay. So that is countably infinite. Okay. Now since B is countable, so it must have an upper bound. Correct. Since B is countable, so it must have upper bound. Okay. Call it one. Call it B, and this belongs to S omega. So what we've done, we choose an infinite subset. Okay. And then we considered a subset of B which is countably infinite. And since B is countably infinite, so it has some upper bound. Call it B belongs to S omega. Okay. Now, so this tells what? This tells that B is a subset of the interval third bracket A naught, comma third bracket B in S omega. Okay. And where A naught is the what? A naught is the smallest possible element is S omega. or A naught is smallest possible element, correct? Now, 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 since the S omega has least upper bound property, okay, so the interval A naught comma B is compact, okay, which is quite obvious. So this tells that B has a limit point x in third bracket A naught comma B. So this tells what? This tells that x is a limit point of A. So this tells that S omega is limit point compact. Okay. So this is the argument. Let me repeat it. Okay. So since A is a subset of S omega be infinite, so we can choose a subset B of A. So we can choose a subset B of A which is countable infinite. Okay. Now since B is countable, so it must have an upper bound. Call it B inside S omega. Okay. Till now this is clear, I guess. Now since B is a subset of A naught comma B in S omega, and A naught is the smallest possible element of S omega. Now, since S omega has the least upper bound property, so this tells that the interval A naught comma B is compact. This tells that B has a limit point x in A naught comma B. And this tells that x belongs to interior of A, which tells that S omega is a limit point compact. So, okay. So this is the full argument. Now, so what we proved is that given space S omega is a limit point compact. Okay. Now we want to prove that S omega is actually not compact. Sorry, I'm not going to prove. It is your home task. So to show S omega is not compact. Okay. So this is the home task. Try to figure this out. I mean, it will be easy, but right now I am not giving the argument for this. Okay. You think about and let me know. Okay. So let's go for the okay. Next question.
Can you repeat the above part?
Okay, sure, Mustafa. Okay, so let me repeat the whole argument once again. Can you please, Mustafa, can you please be specific around which part you have some doubt or some questions? Or should I repeat the whole argument once again?
Whole argument.
Okay, sure. So, 1 minute. Okay, 1 minute, please. Okay, so uh, so what we need to show? We need to show an infinite set must have a limit point, correct? So A subset of A omega be infinite set. So we choose a subset B of A that is countably infinite. Okay, we need to show it admits a limit point, correct? So now since B is a countable set, so it must have an upper bound. Okay, so we call it B belongs to S omega. Okay, now since B is a subset of A naught comma B in S omega, so this tells that A naught, where A naught is the smallest possible element. Now, since S omega has least upper bound property, so the interval a naught comma b is compact. So this tells that b has a limit point x in a naught comma b. This tells that x belongs to a naught, and this tells that S omega is a limit point compact. Okay. So yeah, so that is the thing. Yeah. So so yeah, so this is the argument. So I do understand, Mustaq. Mustaq, I do understand. Or is it that my internet is slow? Which one? Okay, if there's some internet issue, okay, okay, Mustafa. Okay, Mustafa, please let me know, do you understand this argument or not? Okay, okay, but since you are not answering, so let me go for the next question. Okay, so before going to the next question, let me tell you one thing. So we have proved that S omega is not limit but compact. Okay, now but it remains to show that S omega is not compact. Okay, I'm not giving the argument here. You please try to think by yourself and try to figure out why this is a situation. Okay, okay. So now let's go for the next question, namely, okay, okay. The next question is that 1 minute. Okay. So next question is that hmm, okay. Show that 1 point compactification of R is S1. Okay. So that is what? If we have R, sorry. So this is the full R, right? And if we attach 1 point outside it, then it will be S1 only. And this obvious, sorry, this is not obvious, but this thing you need to prove that that 1 point compactification are S1. That is what you need to show. By definition, you cannot prove, right? But so that is you need to show that that is to show there exists a continuous function R 2S1, call it F, such that F of R, such that S1 minus F of R has exactly 1 point. So try to figure out such a map such that S1 minus F of R has at least 1 point. Okay. So intuitively, so instead of writing full line, intuitively, we can write R to be this. This is also R, right? Sorry. So this is also R, correct? Now what do we do? We are adding 1 point here. So this means what? We can join these points, right? So that tells that co- compactification of R is S1. Okay. Now make this mathematical. That is try to find out some F R to S1 having the property that S1 minus image of F has exactly 1 point. Okay. Please take your time, think about it. Uh, okay. And in the meantime, let me think some other questions also. Okay, so 1 minute, please. Okay, so anybody able to figure out or construct any such function? Anybody able to figure out or construct any such function? Okay, so it seems that you are unable to do it. So let me 1 minute. So let me do it for you. Okay. So define. We are defining a map. Define F. What do I? S1 to real line. Okay. Sorry. It should be real line to S1, not S1 to real line. Okay. The map should be T goes to e to the power 2 pi I t. Okay. So check that image of F misses exactly 1 point of S1, which is quite easy. So you can do it by yourself. There is nothing to do actually. So this tells that ace of r minus ace of 1 minus f of r, it has exactly 1 point. Okay. So this tells that 1 point compactification of r is, sorry, it tells that the 1 point compactification of r is s1. So that is the argument. So basically what we need to do, you need to construct a function such that the image of that function union sub point is the given codomain. Okay, that is the way of solving this argument. Understand? Okay. Now I have one question, namely, sorry, 1 minute. Okay, so now let's go to the next question. So next question is that find 1 point compactification of find 1 point compactification of two disjoint lines. Find 1 point compactification through two disjoint lines. That means what? You have two disjoint, of course, finite, two disjoint finite lines. So the, sorry, actually the infinite will work also, no problem. So you have some two disjoint lines and you need to add some point extra to extra point and make it compact. Okay, please, please first think about by yourself, else I shall give and reply or give the argument. Okay. Okay. Anybody have any argument, or can you please tell? At least can you please first guess what will be the one-point compactification of disjoint lines? Okay. So the argument is will be quite intuitive. Okay. And so that's why it is not possible to write things mathematically, but this is what it is. Okay. So look. So there are infinite lines. Okay. So now we can bend these infinite lines. Sorry, it should not join. We can bend infinite lines, correct? That is possible, right? Oh shit. Why it is joining again? Okay. So now, where this first line corresponds to the first figure, second line corresponds to the second figure. Okay. Now, if we attach the put the extra point here, the extra point. Okay. Then then it will be what? It will be this union this, correct? So the figure is this. So this tells what? This tells that one point compactification of disjoint lines is what? Is this figure is known as figure 8. Okay, so this is argument. So basically, we somehow need to cleverly adjust one point to make the whole space compact. So that is the main motivation behind the one point compactness. Okay. So yeah, so this is so that's it. So now let's go for one is uh, okay. So now the next question is as follows. Hmm. Show that the one point compactification of Z plus is homeomorphic with 1 by n belongs to n, union 0. So that is what? That is, you need to find some map if we call the space to be, if we call the space to be y, that is to find a continuous map f from what to where z plus to y such that image of f, that is y minus image of f, contains exactly one point. Okay, so such a continuous function you need to define. Okay, so think about it and let me know. In the meantime, let's think about the next question. Okay. Okay, so let me let me write down the functions for you. Okay. Well, at least some of you should reply for this question, but it seems you are not unable to solve it. Anyway, so let me write on the code. So sorry. So defining f from z plus 2y, the map is n goes to 1 by n. Okay. The z, the domain, has discrete topology. Okay. So this implies that f is continuous. And of course, image of f misses exactly one point of y. Okay. So this tells that there is one point compactification of z plus that will be equal to only y. Okay. So that is the argument. Okay. So I hope this is clear to everybody. So now let's go for the next question, namely, uh, okay. So let me give one interesting motivation. Okay. So so look. So there is one thing we will see later. It is known as quotient topology. Okay. Just try to understand it at least non-mathematically. Okay. Quotient topology. So it deals what? So it deals with the different kind of quotient spaces. Okay. For example, you have a sphere. Okay. And sorry. For example, you have disk. Okay. We have disk. And in the disk, if we if we collapse the boundary, then what we will get? we first get something like that, correct? And then further this boundary is getting collapsed, okay? So finally what we'll get? We'll get a sphere, correct? So that is disk. If we consider disk and if collapse the boundary, then what will the thing we'll get? We'll get sphere, okay? N sphere, okay? But look, this is intuitively obvious, correct? But this is not actually easy to give a proper argument mathematically, okay? So for that, this type of for for dealing with this type of situation, the this one-word compactification techniques comes to the picture. So that is, suppose X is a compact Hausdorff space. The technique is the following. Suppose X is compact Hausdorff and A subset of X be closed. Okay. Then the 1 point compactification of X minus A is nothing but the quotient of X divided by A. 1 minute. Hmm. That is, if X is compact Hausdorff and A is a closed subspace, then the 1 point compactification of X minus A will be equal to X divided by A. So this thing we can directly use to prove that this thing can be used to prove this. Okay, how? This proof I'm not going to. So take X to be this. Okay, and A to be Sn minus 1. Okay, so the previous conditions. So all these conditions are getting satisfied for this example. Okay. Now we need to find dn minus Sn minus 1. This thing is what? This thing is open ball. Okay. Open ball nothing but homeomorphic to Rn. Okay. And so this disk minus Sn minus 1. This 1 point compactification is equal to 1 point compactification of Rn. And this is Sn. So this tells what? This tells that dn divided by Sn minus 1. This is equal to S of n. Okay. So this is the argument. Are you able to understand argument? So basically, what we have done. So first, I observe that if we consider n disk and if we collapse the boundary, then we should get the n sphere. Okay, but and that is what we are getting. Okay, now we need to show this is the case actually. So you consider take x to be dn and a to be Sn minus 1. Okay, then dn minus Sn minus 1 is an open ball which is R of n. So this tells the dn divided by Sn minus 1 is nothing but equal to exactly S of n, and 1 point complex of Rn is less, and that we have already seen. So that is the one possible example of showing that is a good trick. Okay, so we will see this later on. Now, why the quotient topology comes to a fixture in the first place? So for that, suppose hmm, suppose we have some cylinders. Okay, this cylinder can one can get as follows. We have some rectangle. Okay, and if we glue this in the following direction with the cylinder, that means what we're doing, we are doing something like this. So if we identify these two vertex, these two the horizon, the vertical edges, what will be the cylinder? Okay, so of course this is obviously true, but there are certain mathematics, certain topology involved in this type of construction, and this type of construction is the quotient topology. Okay, and this method is known to be cutting pasting technique. Cutting pasting method. Okay, so yeah, so we'll see these things later. Right now, these things, right now, not. So later we'll see. Okay. So right now, there is one important question, and actually interesting question. Question is that show that 1 minute rationals, that is Q, is not locally compared. Show that Q is not locally compared. Okay, it is easy. Um, I mean, it is tricky. It is not easy. It is tricky. Okay. So basically, what you need to do, try to start with the first definition. Start with definition and try to find the contradictions. Okay. So think about it. Take your time. I shall be back in a few minutes. Okay. So can anybody please give the can anybody please unmute yourself and tell the argument? Anybody? Okay. Okay. So in that case, let me write an argument. So before that, let me check the one. Okay. So let me write the argument. Okay. Okay. So assume. So let's start from the definition of Leo compact. Okay. So Q is assume Q is locally compact. Okay. And take X belongs to Q. Okay. So this tells that X belongs to open interval AB intersection Q, which is subset of K, which is sub of Q. Correct. Now, now choose a sequence of rationals in Xn in AB intersection Q. So that Xn goes to X and this X belongs to AB intersection Q complement. Okay, correct. Now, here since K is compact, so this implies that X must lies into K. But K is a subset of Q, so that X cannot be irrational. So there is the argument. So let me repeat. So suppose let's assume that Q is locally compact. Okay, there is X belongs to Q. Okay, this tells that X belongs to open AB intersection Q, subset of Q. Okay, K is a compact. Now we are choosing a sequence of rationals Xn in open AB intersection Q. Okay, in such a way that Xn goes to X. This X belongs to AB intersection Q component. So this tells that X belongs to K, which is subset of Q. So this is the full argument. Okay. So yeah, so this is the argument. Now, so particularly for this problem we have only used the definition of locally compact. So okay, nothing more than that. Okay. Now, 1 minute, please. Now the next question is show that any infinite set in cofinite topology is compact. For with any infinite set with cofinite topology is compact. Okay. So, for this, what you need to do, you need to show that is to show any open cover has finite subcover. Okay. So now try to argue that this is the case indeed. Okay. So you need to start a definition. You need to start with an open cover of this whole space with the cofinite topology, and you need to show that any open cover has a finite subcover. Okay. So yeah, please try to solve it. Okay. So anybody please tell how what will be the argument? Anybody please? So you might have remembered that this problem we have solved previously also, but that is for not general settings. But here this problem is in general setting. Okay. No, no, I mean, Sumesh. So look, what I'm trying to say is that so this problem, exactly this problem we have not discussed. We have discussed a problem similar of this in a particular setting, but this problem is in quite general setting. Okay. So let me tell the argument. Okay. Hmm. So X with cofinite topology. Okay. Of course, is the cofinite topology defined or infinite? So okay, of course there is nothing to mention. It has to be infinite. So okay.
So we have basically idea is
Hmm. Yeah, please.
that X be a infinite set with cofinite topology,
Yes, correct.
and just we consider an open subcover A
Yes,
of X and
correct.
A0 be an
Correct.
element of A. So
Correct.
since X is infinite,
Yes,
X minus A0 is finite.
correct. Correct.
For each element in X minus A0,
Hmm.
choose an element of A
Yes.
containing it.
Yes, correct. X minus a zero finite. So then,
And this result in a finite subcollection of A that still cover X.
yeah, very good, Mustaq. Very good. Okay, very good, very good. Okay, so let me write down the argument properly. Okay. So let U alpha be an open cover of X. Okay. Okay. So we are choosing alpha naught, and so U alpha naught is an open set in X. Okay. So this implies X minus U alpha naught is finite. Okay. So call this finite set contains x1, x2, xn. Okay. So this implies that so all this x1, x2, xn. So each xi belongs to u alpha I for some I. Okay. So this implies what? This implies that x is equal to u alpha naught union u alpha 1 dot 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 union u of alpha n. Okay. So this tells that uh, X admits finite subcover. Okay, so this is the argument. So Mustaq, are you understand?
Yes, yes.
Thank you, Mustaq, for confirmation. Okay. The next question is the following. Show that Hausdorff compact is Hausdorff compact space is normal. Okay. That is what you need to do. That is to show any disjoint closed subsets can be separated by open subsets. Okay. So you need to close disjoint closed can be separated by open subset. This is what is need to be proved. That is what we mean normality. Okay. So now please go use now use whatever the process to look directly. You cannot go with the definitions. Okay. You need to use something. Okay. So let me give you the hint also. Hint. In such a space, a point and a closed set can be separated by open subsets. Okay. These are not open, these are disjoint open subsets. Okay. You try to use this hint and try to figure out or try to give a proper argument of this. Okay. Use this hint for solving that question. Okay. Take your time, think about it. I should about a few minutes. Okay. So, so look. So look, the hint that I wrote is that is I'm not going to explain the hint. Okay. The you should be smart enough to understand from where that line is coming. So, okay. So I'm just trying to course that solve the problem. Okay. So yeah. So with start with two disjoint closed subsets A B of x. Okay, these are two disjoint closed subsets. Okay. Now choose A belongs to. Okay. Now by hint, there is there exist open sets UA. These are open set UA and open set VA containing A and B respectively, such that UA intersection VA empty. Okay, this is possible always. Correct. So, so basically, what is happening? So basically, here is some A. Okay, so there is an okay. So now, so this collection UA forms an forms an what? This collection UA forms an open cover of A. Okay. Now, A is a closed sub of compact space. So this implies A must be compact. Okay. So A is nothing but union of I is equal to 1 to n. Okay. For these AIs, we are having VAIs all containing B. Correct. Now, if we take V to be intersection of VAI, I is equal to 1 to n, then claim is that if we sorry yeah, claim is that U intersection V is equal to empty. Okay. So if T belongs to U intersection V, this implies T belongs to UAI for some I and T belongs to VAI for all I. So this implies what? UAI intersection VAI non-empty for some I, correct? And this is not acceptable, correct?
Yes, yes.
Yeah, correct. Okay. So, by the way, thank you for your response, Mr. Uh, that's what I was thinking in my mind, whether this argument is understandable for students or not. Anyway, so so this tells what? So this tells that this U intersection V has to be empty. Okay, And by construction, U contains A and V contains B. So this is the full argument. Okay. So, okay. So are you understanding the argument?
Yes, yes.
Okay, thank you for the confirmation. Okay. Now let's go for the next question. Okay, by the way, since we start late, so we shall 1 minute. So we shall extend the session for upcoming 7 minutes. Okay, since we have started quite lately. That is, it will be after up to 9:05. Now, okay. The next question is that RK, that is K topology, is connected or not? I mean, of course, it is connected, but show that R with K topology is connected. Okay, think about it. Think about it for a few minutes. Okay. Okay. So, so first of all, look, Rk is equal to minus infinity comma 0, union z third bracket 0 comma infinity. Okay. Now minus infinity comma 0, this is connected as it inherits the topology, and 0 comma infinity connected by same reason. So this tells that third, the closed 0 open infinity, which is nothing but closure of 0 comma infinity. Okay, is connected. Okay, so this tells that, and minus infinity is 0, intersection third bracket 0 comma infinity, this is singleton 0. Okay, so this tells that their union R with K topology is connected. Okay, so this is the argument. Okay, do you understand?
Yes.
Okay, thank you, Mustafa. So basically, this problem relies on the fact that intersection of two candidates is connected and closure of a candidate is connected. Okay. So okay. So okay. Do yeah. So let's check the time also. Okay. That's all for the today's session. Please let me know. Do you have any doubt or any question from today's session? Please let me know. Please let me know. Do you have any doubt, any question from today's session?
No, it's fine.
Okay. Okay. So one minute. Okay, so in that case, we shall meet on the next Friday. And if you have a doubt or any question, you can do an email. I shall get back to you as soon as possible. Okay. Thank you for your time. I'm leaving the session.